So now we're in section 2 of chapter 7, and we're going to start talking about volumes of solids. So there are several types of volumes that we're going to be looking at, and today we're just talking about the disk method. So sometimes it helps to visualize things. So what we're looking at are, if we can take a two-dimensional graph and usually revolve it around either the y-axis or the x-axis, we can generate different shapes. So here are some examples of like items that are made using this calculus, but CV axles or pills, bottles, funnels, all this kind of stuff you're going to see. It might help to kind of visualize and look at what we're actually finding. So anyway, you can create a funnel, for example, if you had a certain curve and then rotated it around, say, a y-axis, that would create kind of a funnel shape. So if a region in the plane is revolved about a line, a solid of revolution is the result. So those are, again, examples are the pictures above. The line the region is revolved about is the axis of revolution. The simplest such solid is a right circular cylinder, or a disk, which is formed by revolving a representative rectangle about an axis adjacent to one side of the rectangle. So what are we talking about? Okay, here's an f of x, just some sort of curve. And if we just think about Riemann sums, the area under that curve is an infinite number of rectangles. So if we kind of blow one up here, look at some sort of rectangle, if I visualize rotating that around the x-axis attached to this curve, it would form sort of this like bullet type shape. But that little rectangle itself would form this nice little disk or this nice little cylinder. And if you had an infinite number of those disks, it would form the shape for this funnel or bullet shape or whatever you want to call it. The volume of one disk would be the area of the disk times the width of the disk. So the area of the disk, if it's a circle, the area is pi times whatever the radius is. Let's call it capital R squared. And the width of the disk would just be whatever width the disk is set to. So we'll just call it W for now. So right now that volume is pi capital R squared times W. Consider the representative rectangle shown in the plane region. When the rectangle is revolved about the axis of revolution, it generates a representative disk whose volume is V equals pi R squared. And rather than using W, if we actually had this like in an XY axis, instead of W, we might call this the distance between two X values, or delta X. On the next page, that's just one disk. If we add up infinitely many of these disks, then we have a solid of revolution whose volume would be an integral. It would be the integral from A to B of the face of the disk, pi r squared, and instead of delta x here, let's put dx. The width of the disk, you can think of it as dx, and we're just saying add up a bunch of those disks, you'll get a total volume there. R is in terms of x. If you have a dx right here. All right, so unfortunately I can't click on this link anymore, but looking at this visual, so if we were to rotate this shape around this line, you're gonna have to excuse my art here, but you'd have all these little circles here, right? So you would get some sort of a funnel type shape. Now, we can also have a vertical axis of revolution. So rather than spinning something around the x-axis, maybe we do it around the y-axis. It doesn't change the formula setup very much. It's still volume is the integral from A to B of pi times r squared, but it'll be dy because r is in terms of y. This is just like we had with the area between two curves. If the two formulas, or if the curves that you're given are already in terms of y, solved for x, then you're going to leave it that way usually. and integrate with respect to y. It just depends on which way we're rotating. So the representative rectangle is always perpendicular to the axis of revolution. So why is that so important? It kind of helps you keep things straight. If you're going to revolve around some sort of horizontal axis, for now it's usually just the x-axis, then your little representative rectangle you can see is perpendicular to that. You're spinning things this way. You get some sort of a little like dome type shape. If you're going to spin around the y-axis, then your representative rectangle has to connect between the axis and the curve, so it's horizontal. And again, that would cause the same shape, but it would be kind of a dome oriented this way. You don't want to overthink these too much. I find sometimes people try to visualize what the shape is going to be, and then they get too caught up in it and make it harder sometimes. Now, these problems are usually calculator based, meaning they're on the calculator part of the AP exam, but not always, and so we're going to do things kind of both ways. So here's our first example. Find the volume of the solid of revolution formed by rotating the region bounded by x cubed minus x plus 1, the x-axis, and the lines -1 and 1. I don't know if you can see this, but this window is set to be -1 to 1. We are rotating it about the x-axis. So if you can visualize this, you're taking this curve and spinning it around the axis. It's going to form kind of a vase shape. You don't have to sketch this. I usually do to try to give myself the visual because I think that's helpful. Or I just think, oh, okay, I'm going to get something kind of like this. If you don't like that, I would say the minimum thing to sketch is pick any point anywhere on the curve, draw your representative rectangle, because that is your R. The height of that rectangle is R, and R is the most important thing. Now, in the next day or two, we're going to be rotating not just around the x or y axis, but around the line y equals 2 or x equals -3, something like that. So when I think of R is always the distance between, distance between the curve and the axis of rotation. For today's purpose, using the disk method, the axis of rotation is always going to be 0, either y equals 0 or x equals 0. So when we define R, which I'll do in my homework, you'll see, R is really just x cubed minus x plus 1. Technically, it's -0 because that would be the distance between, that's the y value minus on the curve minus the y value for the axis of rotation. But anyway, that's R. The volume of this region is the integral from our bounds in terms of x, -1 to 1, of pi r squared. Now, pi can come out here. It's a constant. I always set pi on the outside. And then r squared is x cubed minus x plus 1, the quantity squared, and then we put a dx in there. And I'm going to use my calculator because, again, these are usually on the calculator part, but just like with area, I just don't want to run out of time, to be honest. I want to get through as many examples as we can. Okay, so got an old problem on here. All right, so all I'm doing is, I don't even need the graph. I am typing in pi times the integral from -1 to 1. Don't forget to square r. Now, if you want to put your equation into y1 like we've done before, so you have less parentheses, you could do that and then just put y1 squared on here, and then you don't have to worry about all the parentheses. I'm just going to do that. Okay, so to 3 places, this is approximately, with the pi already multiplied in, 6.762. All right. Next example. Find the volume of the solid formed by revolving the region bounded by the graph of square root of sine x and the x-axis from 0 to pi, which I don't know if you can see this well, but this is 0 to pi right here, about the x-axis. Again, we're rotating this way. If you're going to draw anything, just maybe a little rectangle would be good to help you visualize R. If you wanted to sketch the whole thing out, you've got sort of a little egg shape going on, right? It'd be something like that. All right. So r is the square root of sine x, technically minus 0, because you're saying the distance from this curve to this x-axis. And our volume formula is the integral from 0 to pi of, now I'm writing this for my homework all the time. This is not required for you to show this step, square root of sine x squared. But I did that in my homework keys just so that if you forgot to square something, you would see where we differed. Really, this is just saying the integral from 0 to pi of sine x dx. And actually, I don't want to use my calculator on this one. Integral of sine is negative cosine. Remember, these are not guaranteed to be calculator problems, so it is important that you're able to integrate by hand, not forget how to do that. So this is negative 1, or positive 1, minus cosine of 0 is 1, so minus, there's a negative sign in there already. Ooh. So 1 plus 1, oh, and look what I forgot. Sorry, guys. Pi, 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 pi. The answer is 2 pi. I'm glad I made that mistake, though, because the two most common mistakes are leaving out pi, which I just did, or forgetting to square r, just having pi times r times dx in your integral. All right, next example. Find the volume of the solid formed by revolving the region bounded by 2 minus x squared and g of x equals 1 about the line y equals 1. All right, so this is where that axis of revolution kind of comes into play. So here's the line y equals 1. And here is our 2 minus x squared, right? And so we want to revolve it about this line. So we're talking about the region, bounded by g of x equals 1 and the line y equals 1. So we're looking at this shaded region right here, right, where we hit 1, and rotating it around that axis. I might have sketched that kind of poorly. So we have, again, sort of this like egg type shape, I suppose, football shape, I guess. But here's the thing, that R, your representative rectangle, is not connecting all the way back down to the y-axis, or the x-axis. It's only connecting to this little y equals 1. So when you figure out what R is, remember, it is always the distance from the curve, 2 minus x squared, subtracted from subtracting from this, that little axis of revolution, so minus 1, right? Because think about this. If this height is 2, right here, if this height is 2, then the radius at that point, the radius of revolution, is really just 1 unit. 2 minus 1 is 1. So whatever this height is, you subtract off the 1 so that you're not pulling from the entire x-axis up there. You're just going from 1 to that point. Okay, so I'm going to simplify r. 2 minus 1 is 1 minus x squared. The volume formula, once you figure out r, the volume formula is the same thing every time. Pi times the integral. We're going from negative 1 to 1. I didn't solve that algebraically, but they said the region bounded by f of x and g of x. So if you set 2 minus x squared equal to 1, you will get plus or minus 1. So anyway, of r squared, 1 minus x squared squared dx. And again, for time, just to save time here, try and save time here. I want to type in 1 minus x squared, and I want to square that quantity. I've got the pi multiplied in there already. So this is approximately 3.351. You could also just calculate the integral and say it's that much times pi, either way. Find the volume of the solid formed by revolving the region bounded by f of y, 2 minus y squared, and x equals -3, about the line x equals -3. Okay, so we need to sketch this graph because it's not given to us. Now we need to think about, okay, y minus, or 2 minus y squared is one of those sideways parabolas, right? And the normal y squared parabola is like that. So if it's minus y squared, it really should be opening left. And if you have this 2 in here, you have to think about what that means. Okay, so if I want to think about like the vertex of that, for example, like if I put in 0 for y, if I'm on the x-axis, I get 2 for x. So its little vertex is here, and then it opens left. Okay, so that's the 2 minus y squared graph. And then we're talking about where does it intersect the line x equals -3. So that's like right here. Okay, and we're talking about rotating it around that x equals -3 line. So you're going to get something that looks like this. Ooh, very rough sketch. Something that looks like this, right? But I want to erase that because I made that really messy and crazy. All I really care about is like, what's that little representative rectangle? So give yourself a rectangle connecting your axis of rotation to a point on the curve, and you have to think about what is that r. Now, when you're doing r as a distance between the curve and your center here, you don't want it to come out as a negative. Like you are still doing the point on the curve minus this value. So the point on the curve, my r, is still 2 minus y squared, but I'm subtracting -3. So I'm really adding 3 to that. Because think about this. The distance, if you just do 2 minus y squared and integrate that, you're talking about the distance between the curve and the y-axis. You want to add an extra 3 units onto that radius, so you're subtracting -3. So the r that you're using in your formula is 5 minus y squared. Now everything's in terms of y. So I know that x is -3 right here, but I do not know what this y value is. So if I want to get my limits of integration, they need to be in terms of y. So I know those are both -3, but I have to solve to figure out what y is. So -3 equals 2 minus y squared. Subtract -5 equals -y squared. 5 equals y squared. So this must be square root of 5 and negative square root of 5. Since my equation is in terms of y, my bounds, my limits of integration are in terms of y. So the volume is pi times the integral from negative radical 5 to radical 5 of r squared, 5 minus y squared squared dy. I'm going to do this on my calculator just to, we did this in the area section too, but remember, even though our paper says y, we are typing in the variable as x because our calculator isn't going to be able to switch just to put things in terms of y. Goodness, if I can ever get over there. There we go. So 5 minus, I'm just going to type in x squared, that quantity squared, dx. But we know we're really talking about y's. So the approximate volume is 187.328. Did I put a pi in there? Yeah, 187.328. And these are all volumes. They would be units cubed or cubic units. Oh, that was our last example. Okay, so working on the homework tonight, again, a sketch is not required, but especially on problems like this, where you kind of need to remember what your R actually looks like if it's not just an X or Y axis, sketching the graph is definitely going to help you a lot.